Let us continue with our perturbation method based analysis of differential equations for oscillations. So let us look at this differential equation first. It's the harmonic oscillator forced by something here, a p sine t and a q cos t. The sine omega t is now just sine t, and the natural frequency of this is also the same, it is 1. When you see this, the p and the q both represent what is called resonant forcing. So you can see, if you look at the solution of the differential equation, you find, see, this C2 is an arbitrary constant and it is just sine t. C1 is another arbitrary constant and it is cos t. Okay, and there is a q minus pt over here, doesn't matter. If q is there, then t sine t is there. You cannot avoid it. Okay, resonant solution. And this q can be, this q times cos t, it can be cancelled or absorbed into this cos t over here, but the minus of p t cos t is another resonant term. Okay, so that is, these are terms that grow linearly in amplitude, and they are called resonant terms in the forcing, and these growing terms are called secular terms for historical reasons. Okay, so they are called secular terms for historical reasons. Okay, so let me now move to the equation I really want to study, which is this. And then over here, let me add c times diff x of t. Okay, so there's damping and there's a cubic term. Okay, so this is the damped forced Duffing oscillator. Now I want to study this using a perturbation method, and the way I will do it is I will think of it as lightly damped, I'll think of it as weakly nonlinear. Okay, so just to remind myself that there are these small things here, I will assume that the damping is epsilon times c. Epsilon is a small quantity, c is order 1. When I do this, okay, so now this is a small term. Okay, let me try a solution. Now my assumption is that because the forcing is sine omega t, there is a solution with the same period. Remember, we did the same already with harmonic balance. Over here what we will do is we will say x approximate is equal to add capital X k of t times epsilon to the power k, k equals 0 to 1. Let me just use the first order. So I can have more terms, but let me begin here. Okay, very good. Then I say dEA is equal to expand, substitute x of t equals xa in dE. We have been doing this already. We say convert Taylor epsilon to polynomial. Right. So over here, because it is on two sides of the equal sign, it doesn't like it. What I will do is I will make this a minus, and we will say that basically that quantity is now 0. When I do that, this will work. Okay, and you see this is the small correction term, and we look at this part and there is no problem. Then we come here and we say, let's look at the coefficient in dEA of epsilon, the power 0, and then we say D solve that for capital X 0 of t, and here is where we run into trouble. So first of all, sine omega t, if omega is not 1, then these have to be thrown away, okay, because they are a different period. Okay, I'll throw them away. But over here, when omega is 1, it blows up. I have an infinite amplitude, and then I don't know what to do with this. My whole interest is near the resonance, and I am not able to capture it. Why is that? It is because when I treat this as small and this as small, my unperturbed problem is this resonantly forced undamped oscillator, and that has a very large amplitude. This is why I will not be able to do this. In this way, I will not get a meaningful analysis here. Okay, so what I will do then is I will say that omega is actually close to 1. Okay, so what I will do now, and I will say that the forcing amplitude is small. So let me make a new differential equation over here, and I'll call this dE1 just to distinguish, and I will say here epsilon times, okay, and then I will say this omega, I will replace it with 1 plus epsilon times capital DELTA. Okay, so you see now my omega is close to epsilon. If delta is bigger, that means I'm positive, that means omega is slightly more than 1. If delta is negative, that means omega is slightly less than 1. Now, as you have seen in the previous lecture, this is not easy for me to expand, right? So actually what I should do is I should define a new tau. That tau is 1 plus epsilon delta times t. What that means is, let me write it here so that you will, what it means is d by dt of something is 1 plus epsilon delta times d by d tau of something. That's what it means. So here we will come here and we will rewrite this like this. We will say 2 and say tau 1 plus epsilon times delta square times, and then 1 plus epsilon times delta times, this is going to be tau, this is going to be tau, this is going to be tau, this is going to be tau. This is my new differential equation. So you see I have replaced it, right? What have I done? I have said tau is 1 plus epsilon delta times t. That means tau over 1 plus epsilon delta is equal to t. And that is what leads to this multiplying factor for the second derivative with a square there, this multiplying factor for the first derivative, and now this system, I am in a place where I can start working with this. Okay, so that's now this is in the tau time, and in the tau time my periodic solution always has a frequency, angular frequency 1. Okay, alright, let's begin here. So once again I will come here, I will say XA but what I will do is over here I will say tau. Okay, so this is my solution. I can have more terms, but you will realize soon that this is all I need to get a meaningful approximation. So then I will say DE, I'll just copy that here. This is my DEA now. X of tau is that. Okay, very good. That didn't work. That is because this is supposed to be D2. Okay, good. And now you see that resonant forcing from the first order equation has disappeared. This is the order epsilon term. Over here, the forcing is also there. The detuning, this delta is called a detuning. Let me write it here so that you can see. It's a detuning parameter. Okay, so that one is in here. Your damping is in here, your nonlinearity is in here, and now it is easy for me to see that the solution for x0 is a sine tau plus b cosine tau, but at this order, at order epsilon to the 0, or at order 1, I am not able to say what is a and what is b. Let me remind you, I have started with this equation, and I have said that I will look for periodic solutions. Then I have come here. Over here I had said damping is small and nonlinearity is small. I came here and realized that I have some troubles, and I said, okay, what I can analyze is the forcing being small, the damping being small, the nonlinearity being small, and the frequency being close to 1. Then I have stretched my time so that I have this equation here, but I am still looking for a periodic solution. In that periodic solution, over here, all I have is a sine tau plus b cosine tau. That's what I have. But I don't know yet. At order 1, I don't know what is a and what is b. Okay, very good. So I come here and I say temp is equal to, and I say x0 of t is equal to a times sine of tau, well that's tau, plus b times cosine of tau. Okay, then I say DEA is equal to expand, substitute temp in DEA. Okay, and then it's all order epsilon here, you see, so I can say collect epsilon. Okay, and then I can say this is what I have to solve now. Okay, and now it has got this cos cube tau and sine tau, cos square tau. It's got all these things here, but what I will do is I will say temp is equal to the coefficient in the previous of epsilon, but what I will do is I will say combine with trig identities, and you see now here is x1 double dot and here is x1, and the rest are like forcing terms. And when I study the forcing terms, I can come here and I can say the coefficient in temp of sine tau, and I get something here, and I say the coefficient in temp of the cosine of tau. You see, and then here is the point. So if this thing times sine tau is present in this equation, then x1 cannot have a bounded solution. Remember, I have started by saying that there is a periodic solution and I am going to find it. I have not said anything about whether the periodic solution is stable or not stable, but I have assumed that it exists. I insist on a periodic solution. Since I insist on a periodic solution, I have been led to the conclusion that this must be 0. Similarly, the cosine of tau coefficient, which is this, has to be 0. I have been led to the conclusion that if there is a periodic solution, then this must be 0 and this must be 0. I go back just one step in my calculation and I was in a situation where I didn't know what A and B was. Well, now I have two conditions. This is what A and B have to satisfy. If a periodic solution exists, and I will ask you to look at the harmonic balance equations that we had and see the relationship with those. Okay.